Welcome to topic 3.15. This is the last new topic in Unit 3, which is the last new topic covered on your AP exam. So this is the last lesson for this quarter. Next class, we will review for the SAT, because it will be the day before the SAT. And then we will test after the SAT, then it's spring break. Holler. Quarter 4, we're going to spend a lot of time reviewing for the AP exam. So this is the last new topic that is on your AP exam in general. As we did with most functions that we learned about, we discussed the function, we talked about its shape, we talked about different things, and then we talked about the rate of change of those functions. We're going to do the same thing for polar functions. Now, very similar to what happened last class, discussing rates of change on a polar coordinate grid is confusing because we're not used to it. So we will be switching things back to the rectangular version to be able to answer a lot of these questions, especially when it's a visual question. In this section, we will learn ways that we can describe characteristics of the graph of a polar function. Given a polar function r equal to f of theta, we know that r, radius, it actually represents the signed radius of the function. We use this phrase signed radius because we know that r can be negative or r can be positive, even though radius is a distance and distance is always positive. It gives us a direction for our radius. As we trace the graph of a polar function, we are interested in whether the graph of r equal to f of theta is getting closer to the x-axis, to the origin, or further from the origin over a given interval. So we're going to be talking about whether the function the radius is getting closer to 0, the origin, or getting further from the origin. That's going to be the goal for today. We're going to skip the little table for a second so that we can color code these two graphs. Now this is going to be different than how we color coded last time. Last class I had to split the rectangular function into 4 pieces based on the parts that were increasing concave down, decreasing concave down, decreasing concave up, and increasing concave up. I am going to color code this one differently today. Today is all not about the midline, but about the x-axis. So I want you to highlight the x-axis in yellow. This is what we're comparing our function to. We're going to compare it not to the midline of the function like we did last class, but to the x-axis itself, to the zeros of the function. And if this is the case, if I'm looking at the rectangular version of 1 plus 2 sine of x, we have this first section right here that is above 0 and increasing. Above 0 and increasing. If we're going to find this section that is positive and increasing, so above 0 and increasing, on the polar function, that's going to be the section from angle 0 to angle pi over 2. Because if you notice, this is angle 0 and this is angle pi over 2. This feels familiar. This is what we did last class. I hear you. But this next section, the section that we're going to highlight next, watch where I'm highlighting because it's not right in an order. We're going to highlight the sections that are positive but decreasing in blue. On my rectangular graph, the next particular section is positive but decreasing. And it's positive and decreasing all the way until we reach that x-axis. After we touch the x-axis, when we cross through it, our values are now negative. So our only blue section, or our blue section, is a little bit bigger than we would have highlighted it last time because we were looking at the midline last time. We're looking at the x-axis this time. And we're seeing that those angles go from pi over 2 to 7 pi over 6. So watch how much I have to highlight here. Here's pi over 2, and we're going all the way to 7 pi over 6. So look, it did go below the x-axis or the r-axis. R-axis may be the wrong term, but below what was the x-axis on the polar function. After this, we would describe the next section of the rectangular function as this itty-bitty section that is negative and decreasing. So negative and decreasing. That section that is negative and decreasing goes from 7 pi over 6 to 3 pi over 2, and it is this section from C to D of the polar function. The next itty-bitty part of the rectangular section is going to be the rectangular part that is negative but increasing. So the outputs are negative, but we are getting bigger we're getting less negative. So negative and increasing goes from 3 pi over 2 to 11 pi over 6. So that's the other side from D to C of the little loop of Delaunay. There's like a tiny little piece we haven't highlighted, correct? Yeah, let's describe this. If you were to describe this using positive or negative, is this section, are the outputs positive or negative? Am I increasing or decreasing? What color did I use originally to do positive and increasing? Pink. So this guy's also pink because we're positive, we're above the x-axis, and we're increasing. Do you notice there's like a tiny little section of the polar function we had not highlighted yet? Yeah, that's from C to A. You had already highlighted it? Oop, good thing it was right. Now, what are we trying to show here? Remember, the object of these descriptions is to describe whether the graph is getting closer or further from the origin, aka the distance is increasing or the distance is decreasing between the radius and the origin. This is hard to see on a polar graph because we're not used to it, unless we're following the counterclockwise motion of whether we're getting closer to or further from the origin. It is a lot easier to translate this into rectangular to see, but all of these sections that we've highlighted mean the same thing. All of the pink sections, aren't we getting, bless you, further away from the x-axis on my rectangular? So further away, further away. Notice we are also getting further away radius-wise. The radius is getting bigger as we go around in the pink section. We're getting further from the origin. In the green sections, this is also getting further from the origin. Because if you notice, we're getting further away, but they're underneath it. Further away. And look, further away. The radius is getting bigger. For the blue and the purple sections, we're getting closer to the origin. We're getting closer to the x-axis. We're getting closer to the x-axis. So in the blue sections, we're getting closer radius-wise to 0 and closer radius-wise to 0. These are the ways I'm going to ask you to describe the graph or read a graph to describe what it might be doing, is whether the coordinate points for the radius are getting further or closer to 0, which is the origin on a polar function. Okay, when stuck, it is easiest to take the polar function and graph it as a rectangular to see what's happening. In example 1, that's exactly what we did. It says the graph of the function f of x equal to 3 times sine of 2x. So this is a sine function with a period of pi, because it's 2 pi divided by 2, and an amplitude of 3, so max 3, min negative 3. The graph of this function where x is between 0 and 3 pi over 2 is shown above, but it's to the right. Oops. In the rectangular coordinate system, if the polar function version of this, notice it changed to r and theta, is graphed in the polar coordinate system between 0 and 3 pi over 2, which of the following intervals is the distance between the point with polar coordinates f of theta comma theta and the origin decreasing? We are looking for where the radius would be decreasing, which means we can look at the rectangular version of this polar function and see where the distance between the function and the x-axis is decreasing. So let's go ahead again and highlight our x-axis. We're just going to highlight in the correct color scheme the sections of this graph where we are getting closer to the x-axis. This first section right here, are we getting closer to or further from the x-axis? Further from. How about this one? Closer. And it's the blue kind of closer from a positive and decreasing. So I'm going to highlight that blue if you followed my color scheme. Then we cross over the x-axis. Are we getting further or closer to the x-axis here? Further. And then I turn this corner. What about this one? Closer. That was the purple because it's negative and increasing. The next section, I crossed over the x-axis, so I have to change. Is this one getting closer or further? Well, what about this one? Closer. And that's back to being blue, if you followed my color scheme. So we have these two colors, blue and purple, that are describing where the distance between the x-axis and the function is decreasing, which translates to the radius decreasing if it's a polar function. So we just need to pick an answer choice that's one of these three sections. So we either want to answer between pi over 4 and pi over 2, between 3 pi over 4 and pi, or between 5 pi over 4 and 3 pi over 2, which means that we would answer with C. That's the only section that I've highlighted where we are actually getting closer to the x-axis, which would mean I'm getting closer to the origin. You actually do not get highlighters on the test.
Oh my gosh. Can we have highlighters on the test?
You cannot have highlighters on the test. You are only allowed a number 2 pencil.
Can I use a pen?
No, it's pencil. Well, actually, I think you can use a pen. I will double check on that. I can't remember.
Is it just black pen or can it be like...
I will double check on that. I don't know. So reminder that this test is hybrid. So the questions will be given to you online anyways. So you will have to write them down on your paper, which means we can take every polar graph and instead of trying to graph it like a polar function, we can just make it rectangular on our piece of paper to do our work. Okay? So yes, you do only get pencil, which means when we start reviewing, the highlighters go away. For learning, it's better to learn in colors, but then we're going to have to start reviewing in just pencil. I'm so sorry. Perfect. Hopefully this is the calculator section. It's not. The second thing I'm going to want us to be able to do to describe on these polar functions is talk about the relative extrema of polar functions. Now, again, the definition that's actually written here is kind of confusing for what a relative extrema is. What I want you to do is not overthink this. This is the same graphs from the front. Without spending too much thought process, if we look at the rectangular version, where is the maximum, relative maximum of this function? Yeah, well, coordinate point wise, what would be that coordinate point? Pi over 2, comma 3. Right? That's a maximum point. We know this. That also means that at the polar coordinate 3 comma pi over 2, we also have a maximum. So if I go to 3 comma pi over 2, that's right here. That's the same maximum point, just now in the polar function. Okay, don't overthink it. In the rectangular function, where is the relative minimum? Agreed. So this is now a relative minimum right here. So that means that the polar coordinate, -1 comma 3 pi over 2, will also be a minimum for this graph, which means right here, this is a minimum. The definition says, and I'll read it once for you, it's a little confusing, so I just want you to think again, back into rectangular, they're the same coordinate points. It says that if r equal to f of theta changes from increasing to decreasing or vice versa, then the function has a relative extremum on the interval corresponding to a point relatively closest to or furthest from the origin. Or, graph it rectangularly, find the coordinate point of the max and mins, it's the same coordinate point in polar. Just now it needs to be r comma theta instead of x comma y. Are we okay with that? Great. So here's a question that we might see. It says, consider the graph of the polar function r equal to f of theta, where f of theta is equal to 1 minus 2 sine of 2 theta in the polar coordinate system between 0 and pi. Which of the following statements is true about the graph of r equal to f of theta? I don't want to visualize what this looks like. This is on the non-calculator portion of the test. I can't use my calculator or Desmos to see what that polar function looks like. So instead, we're going to sketch 1 minus 2 sine of 2x. Here's some things we need to know. What is the midline of this function? It's at 1. How do I know that? Because we added 1 to the function? Because, what's the amplitude of this function? 2. It's negative though, so what does that mean? I hear yes, the function has been reflected. So that means instead of sine immediately increasing, sine will do what? Decrease. But we are starting at a midline. We also know that it has a period of 2 pi divided by b, which means the period is pi. So I can have 4 intervals between 0 and pi, and I will see the whole thing. My function looks like this. I have a midline, and then a minimum, a midline, and then a maximum, and then another midline at pi to complete the entire shape.
Yeah, so I was thinking.
So questions for you. On our rectangular function, where is the relative minimum?
Right there.
Well, right there, without working too hard, it's right there. Bless you. It would be pi over 4, comma, negative 1. How did we get pi over 4? I know I wrote that really small. I'm sorry. I'll zoom in. Yeah, this is pi now split into 4 pieces. So this is pi over 4, which means what's this? 2 pi over 4, which is pi over 2. What's this one? And that's where our maximum value is, correct? We have a maximum value at 3 pi over 4, comma, 1, 2, 3. Okay, let's look at what the answer choices even offer us here. It says the graph of r equal to f of theta has a relative minimum on the interval between pi over 3 and 2 pi over 3. We have a relative minimum between 2 pi over 3 and pi. We got a whole lot of words happening here. But let's think about this second part of the sentence. This one says because r equal to f of theta changes from negative to positive, it changes from increasing to decreasing, negative to positive, increasing to decreasing. So maybe we should look there to see if we can eliminate something. When we have a relative maximum and minimum, is it because the function changed from being negative to positive? Or is it because we changed from increasing to decreasing or vice versa? Increasing, decreasing, which means these two answer choices are like never going to be correct because that's not how you have maximums or minimums. That's actually how you have zeros of a function. When we go from a negative to a positive, it means we have to cross the x-axis. So like there's no way it's A or C. So we really only need to look at whether we have a relative minimum or relative maximum between 2 pi over 3 and pi. Where is 2 pi over 3? That's such a great question. Let's figure it out. And in a pinch, this is what I would do. If we are trying to compare, let's say, pi over 2 compared to 2 pi over 3, mathematically, we need to have them have the same denominator to do this comparison. What would be the common denominator here? 6. So this is 3 pi over 6. What would this one be? 4 pi over 6. So which one's bigger? 4 pi over 6, which means that this value is somewhere here. So if we go from somewhere here to pi, is that a maximum or a minimum? Maximum. So we can answer this question as D, that has to be a maximum because we're looking at the end of the graph. So yes, you do need to sometimes compare the fractions together, give them a common denominator so you can actually tell which one's bigger or smaller, so you know where that point is on your number line. And then we get to the big kahuna. Average rate of change on a polar function. You guys know the formula for average rate of change. I've asked you so many times, right? Yeah, every formula quiz, it's been there. It's right here for you too. So for polar functions, we can also find the average rate of change. This is not easily done visually. This is much more easily, that's not how you say that sentence. Oh, ignore. It's much more easily done analytically, meaning by hand. But the formula is the same. You evaluate the function at the second input. You evaluate the function at the first input. You subtract them, divide by the difference in the inputs. We know this formula. So if we're asked a question like number 3, I guess we should highlight this formula even though I know you know this. Okay. Consider the graph of the polar function r equal to f of theta, where f of theta is 3 minus 3 cosine of theta in the polar coordinate system. What is the average rate of change of r equal to f of theta over the interval from pi over 2 to pi? This is x1. This is x2. So if we were answering this question based on the formula you've written down 1,000 times for me, we would say the average rate of change would be equal to, what's the name of the function here? f of, what is x2? B, pi, minus f of x1, what's x1? Pi over 2. All divided by what? Pi minus pi over 2. This is exactly the formula you've written down for me 1,000 times. However, we do need to evaluate for the numerator here. To make this easier on ourselves, we're going to do that on the side here. We're going to do like a little sidebar. We're going to figure out what f of pi is on the side so we don't like have messy algorithm over here, messy algebra. Which means I'm going to take the number pi and I'm going to plug it into the function. 3 minus 3 cosine of pi. Ooh, aren't you glad I asked the questions I asked at the door? What is the cosine of pi? -1. What is negative 3 times negative 1? 3. So that means this evaluates to 6. Oops. If we do this again for the second function, or second value, we're just plugging in pi over 2. What is the cosine of pi over 2? 0. So this is 3 minus 3 times 0. What's 3 times 0? 3 plus 0 is? Boom. So now I have the values, the outputs of the function when I have plugged in pi and when I have plugged in pi over 2. So we can go back over here. We already answered this question. What is f of pi? 6. What is f of pi over 2? 3. And then, oof, I have to subtract a fraction down here. What do fractions have to have? Which means I'm going to change this to 2 pi over 2 minus 1 pi over 2. Now they have a common denominator. 6 minus 3 is 3. 2 pi over 2 minus 1 pi over 2 is pi over 2. Ugh, got a denominator with a fraction. What do I do? Thank you for not saying panic. We keep, change, flip. I'm going to come down here. We keep, we change, we flip. This becomes 6 over pi. That is the average rate of change. Good morning. This is the average rate of change of the function between pi over 2 and pi. Questions, comments, concerns? Yeah, unless this is the calculator section of the test, they're going to leave pi in it because you're not going to multiply by pi in your head because you'd only use probably 3 decimals and it would be off. But if it's the calculator section of a multiple choice, that means if you see decimal answers, throw that into the calculator. How do we feel about average rate of change? We've been writing down the formula for long enough, we forgot how to use it maybe, but now we've seen another one. Example 4, and you're going to want to write with small handwriting here. I gave you enough space, but don't get crazy with your handwriting. It says the table on the right gives values of the polar function r equal to f of theta at selected values of theta. Use the average rate of change of r equal to f of theta over the interval pi over 6 to 7 pi over 6 to approximate f of 5 pi over 6. Whoa, what is this even asking for? This is asking for us to predict a value using the average rate of change. Y'all remember that formula that I asked you to write down 1,000 times to predict a value using the average rate of change? It was y equal to the average rate of change, open parentheses, x minus x1 close parentheses, f of x1 or y1. Okay, great. That's awesome. That's the rectangular version. Do we use x's and y's in the polar coordinate system? No, so we're going to change this to r equal to AROC. AROC stays the same. And it's going to be theta minus theta 1 plus f of theta 1. It's the same thing. Sure. Great. So we need some things to plug in here. One of the things we're going to need is the average rate of change. So we'll have to find that. We will also need an input value and an output value. But like, look, here's an input value, here's the output value. So I already have that. I do need the average rate of change, though. Didn't we just practice how to do this? So the average rate of change will be equal to the values that I was given, pi over 6 and 7 pi over 6. This will be f of 7 pi over 6 minus f of pi over 6. It does give us the values. We don't have to plug this one in because look, it gave it to us in the table. Let me fix my handwriting. This looks messy. What is f of 7 pi over 6? -1. That's from the table. What is f of pi over 6? 2. And then I need to subtract 7 pi over 6 minus 1 pi over 6. Can I subtract those already? Yeah, what is 7 minus 1? So the 6 pi over 6, what does that become? Pi. Okay, that's nice. So I have -1 minus 2 over pi. That's -3 over pi. We have our average rate of change. We have a set of inputs and outputs. We can plug in to predict the future. What? So that means that any radius that we want will be found by doing -3 over pi multiplied by some angle minus pi over 6 plus 2. That's our equation that we can use to predict the future. But it does ask me to actually predict the future to approximate a value. What does it want to know the output for? 5 pi over 6. So to actually answer this question, to answer f of 5 pi over 6, that means I'm going to do -3 over pi multiplied by the angle 5 pi over 6 minus 1 pi over 6 plus 2. What did I do there? Yeah, I just plugged it in. If we have an equation that will predict the future, we can use that equation to predict the future or predict a value. It may not even be outside the range. Okay, math time. Start on the inside. PEMDAS tells me to deal with the parentheses first. What is 5 pi minus, oh my gosh. Let me say these words correctly. 5 pi over 6 minus 1 pi over 6. 4 pi over 6. So I end up with -3 over pi multiplied by 4 pi over 6 plus 2. It does reduce to 2 over 3, but give it a second. What do you notice is on the numerator and denominators here? What's on both the numerator and denominator? Pi. Oh, snap. So what will happen if it's on both? They will cancel out. So we can cancel out the pi's. And if we just do regular math, and I know this can reduce down, but I'm assuming we might have panicked and not seen that, so we're going to leave it not reduced. This would end up being -12 over 6. Where did I get the -12 from?
3 times 4.
Okay, what is -12 over 6? -2. And what is -2 plus 2? 0. So when we plug in the angle 5 pi over 6, this polar coordinate would probably be 0, which means we'd be at the origin. So a lot of the things that we did with rectangular functions, aka describe whether it's getting closer or further from the x-axis, from the zeros, talk about the maxes and mins, and or do the average rate of change, still applies to polar functions.